Okay. So, chapter 8 is kind of the last part of comparative statics. We're going to put some more general functions, some more general ways to look at things. And then 9, 10, and 11, we start looking at taking functions and figuring out ways to constrain them. Like maybe a little more what happens in the real world. But we need the basic fundamental how do things work. And there's some other interesting stuff about uh, differentials and total derivatives that we like. Okay. Okay. The differential. Look, two things are going on here. One is the fact that things are often interrelated. That when we do a partial derivative, we're separating out the effects, but sometimes those effects interact with each other in ways that you can't pull it out just by looking at that partial derivative in isolation. The other thing is we tend to look at that as just a thing, right? That's just a meaning, right? We say, oh, that's just f of x. But, 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 it is actually possible to look at this as a fraction of two what we call differentials. So the derivative is the ratio of these two, differentials. So let's say that we have this equation. And we say, look, dy dx, what is that? Well, it's going to be 4x plus 5. Well, it turns out that we can also say that dy equals 4x plus 5 dx. And you're saying, well, why do we want to do that? Well, what this explicitly is telling us that a change in x creates a change in y, and this is the value of how it does that. So it's laying out this change in x, creating a change in y. Is that exciting? Okay. It's still all about slopes and tangents, and you can read all the stuff there is to read if you really, feel like it. But yeah, it's fun. Fun. Okay, so we'll be back to more of that here in a second. But how this works, why we talk about these things this way, is, for example, probably the most common example that people use is with elasticities. Because if you remember price elasticity of demand that you learned in principles class, it's the change in Q divided by Q over the change in P divided by P. The percentage change in quantity divided by the percentage change in price. Well, guess what? If we take those deltas and turn them into D's, in other words, we go from the small change that you get with a delta to the approaches zero change that the D implies, right? So you get dq over q, dp over p. Okay? Now you can rearrange that mathematically and say dq dp times p over q. Well, now I have a calculus-looking thing here in the middle of my elasticity. Okay? So if you had just thought of, dy dx or dq dp as being just this marker that sits there on the left-hand side of the equation that told us we did something, you need to rethink and think about this as something we can actually do stuff with. Okay? Yeah, you're like, really, I didn't want to do stuff with this. Well, if that's my demand curve, dq dp equals minus 10, right? 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 Q over P equals 200 minus 10P divided by P. So, yes? So we get elasticity equals minus 10 times P over 200 minus 10P. Yes? Yeah? Okay. No? Minus 10P over 200 minus 10P is P over 200 minus P. So now, that's the elasticity at any point on the line. All I have to do is take a price, stick it in there, and out pops the elasticity, the point elasticity, right? Before, we would always do this in principles class. You always do this by calculating an arc elasticity. So we'd always say, this point minus this point, the midpoint, the edge. And we left point elasticity. We said, look, we don't calculate point elasticity because it's too hard. Well, it's actually not too hard, but you have to understand calculus to do point elasticity. So you're saying, well, this is simple. You could, no, because sometimes that demand curve might be a function, right? And so the first derivative here, this derivative might not be a constant. In fact, it's probably not a constant in real life. It's probably a formula, a function of its own. And so the point elasticity formula gets complexical. But the point is that the point elasticity formula comes out of changing so that we get that, right? I'm blaming you guys. Yes. That is a much better formula for elasticity because it's a point elasticity formula instead of an arc elasticity formula that we've used before. Is that exciting? Okay. You're like, no, I really didn't think that was exciting. But yes, that really is exciting. Really, really is. Like, really is. No? Okay. I'm way more excited about this than you are. And I don't know why. But I am. Okay. So let's just take this a step further for a second and think about if I have z is a function of x and y. Okay? I can write what's called a total differential. And the total differential is something like dz equals fx dx plus fy dy. Okay? Where f is the first, that f represents the first derivative, right? So your dz equals dz dx dx, kind of. All right? But don't write it that way. Write it that way. The partial and the partial. Okay? Or you could say dz equals the partial of z with respect to x dx plus the partial of z with respect to y dy. Okay? And we can do that and create this amazing little formula that, well, what's that look like to you? He said, what's that look like to you? Does that look like a regression equation to you? Well, it might. Okay? And what is this equation telling us? Let's write this out again. And some people will write it this way, with these two things representing the partial derivatives. I'm writing this out. You're saying you've written this out 3 different ways. Yes! Because you never know how peoples out there in the real world are going to write this out. So understand that there's multiple ways that we might just write this thing out. Okay? And you can write it out just one way because that's how you feel. But what is this? Definitely looks like a regression equation, right? This is the effect of a change in x on creating a change in z. And this is how a change in y creates a change in z. So if you're saying, that really does seem like what you might do in a statistical analysis, yes, it is. Okay? Very often we're going to take, in the real world, we would develop a theory. Remember when we talked about econometrics before relative to mathematical economics, and how the bad econometrician gets a bunch of data, plugs it into a computer, plays around with it until they get an answer. The good econometrician develops a theory which gets expressed in an equation or equations, which then they go figure out a way to test statistically. So we like to have these things like this that look kind of like regression equations, because that helps us move from A to B. Okay? And if you're saying, give me another bad example, weird example, let's suppose we have this. And this is a production function. Okay? So this is output of our factory is a function of how much capital and labor we have. Okay? Is that exciting? Okay. So I could find something that looks like this. Now you're saying, what the heck is that? Well, this is the change in output for changing the amount of capital and changing the amount of labor that's involved. Okay? And so I can find the partials, right? This is the partial of Q with respect to K. And this is the partial of Q with respect to L. Well, we have a name for this and a name for that. What are those names? Those are the marginal product, okay, in this case of capital, and yeah, I wrote that with a K, but you can write it with a C if you feel like, and over here of labor. So I have the marginal product of capital and the marginal product of labor affecting the output. Okay? Is that exciting? So if I have this equation, right, I find dq dk is 36L minus 4K, right? And dq dl equals 36K minus 9L squared. Okay? This is MPK, and that's MPL. So I can look at this now and I can say, well, what effect does a change in capital have on output? Right? Q dq equals, right? Yes, very exciting. So what effect does a change in capital have on output? Well, the effect of a change in capital on output is the more labor I have, the better the effect of, the stronger the effect of a change in capital has. But the more capital I have, the weaker the effect of a change in capital. That's logical, right? There's an economic explanation there, right? If I have a bunch of labor but not much capital, if I have a bunch of workers and not many shovels, adding shovels is helpful. If I have 800 shovels and 2 workers, adding shovels is not very helpful. All right, so the marginal product of capital increases as labor increases and decreases as capital increases. And the opposite happens for labor. The marginal product of labor increases as the amount of capital increases, but decreases as the amount of labor increases. And now, again, going back to Alfred Marshall, I can tell a story here from the math. And because I can tell a story here from the math, I'm thinking that the math tells me something that I can test, right? Now I can go out and test this math. Yes? Are we excited by that? Yeah, we are. So I can go out and test the math, right? And by testing the math, now I get something exciting. Okay?